The Michaelson Interferometer has been a very important instrument with respect to the theories of relativity. When it was first used, the interferometer was used to show that the speed of light was the same in all directions, in all frames of reference. This is the first postulate of special relativity. Today, the Michaelson Interferometer is used to measure gravitational waves at different observatories throughout the world, such as LIGO and Vigo. Now, the Michaelson Interferometer is a very simple optical device. Basically, we're taking a coherent source of light and splitting it along two path lengths. We send it along one direction, reflected off a mirror, and then recombine it along another leg in another direction, where it's observed to either constructively or destructively interfere. Again, it was very important to show that the speed of light was the same in all frames of reference. This disproved the existence of the luminiferous ether, which was thought to be the medium through which light traveled. We can also use it to measure the wavelength of light and even the speed of light. And as we said earlier, it's used to detect gravitational waves at gravitational wave observatories. Now, here's how it works. We have a coherent source of light. Originally, this was a bright source of light that was filtered to produce one wavelength. The light is sent to a half-silvered mirror. This is a mirror which has a very thin coating of metal. The metal is thick enough to reflect some of the light, but not so thick that some of the light doesn't pass through. It splits the beam about 50-50. 50% of the intensity goes down this arm, 50% of it passes through the half-silvered mirror and goes down this arm. Now, at the end of this arm is a mirror. This mirror can be moved forward and backward. At the other end is a fixed mirror. If the path length of L1 and L2 are identical, then when they arrive back at the beam splitter and are sent to the observer, the two beams will be in phase and they will be coherently combining to produce constructive interference. We'll see a bright fringe. If, however, we move this mirror by a quarter of a wavelength, we've introduced an extra distance that this wave has to travel. Therefore, 1/4 wavelength plus 1/4 wavelength extra path length difference is going to put this wave 180 degrees out of phase with this phase right here. When an observer sees the light, typically what they see is a bullseye pattern. This happens because if one arm is slightly longer than the other arm, the angular difference, the angle at which the light is returned, is slightly different due to the different angles. Basically, the light that travels a greater distance is going to come in at a slightly less angle. The light that travels a shorter distance has a greater angle, and this means that there's an angular difference between the path lengths of the light. What's important is that what is at the center of this pattern. At the center of this pattern, we see a dark fringe. That is because the path length difference between this leg of the arm, the blue leg, is 1/4 of a wavelength difference compared to this leg right here. So again, when we move M1, the movable mirror, 1/4 of a wavelength, we go from a light fringe to a dark fringe, or a dark fringe to a light fringe. So we can effectively measure the wavelength of light this way. Alternatively, because the speed of light is equal to the wavelength times the frequency, we could use this to measure the speed of light if we knew the frequency of the wave, and we're able to measure the wavelength using the interferometer. Once again, here's how this works. We can imagine that if both waves travel the same distance, both are going to have the same phase, both are going to constructively interfere. Again, this occurs for a path difference of not only zero difference, but also any integer times the wavelength. If the path difference is an integer plus 1/2 times the wavelength, which would correspond to a mirror difference of 1/4 of a wavelength, then you're going to get a dark fringe. Now, once again, the first implementation of this device was by Albert Michaelson and Edward Morley. Morley, actually a Newark, New Jersey native, who built this device to essentially try to measure the luminiferous ether. They're trying to see whether or not they could detect a change in the speed of light as the Earth went around the sun. As the Earth moves through space, the idea was it was moving through this ether. If it moved toward the ether, then basically the wavelength would be compressed, and they would measure a shorter wavelength in that particular direction. As he moved with the ether, the wavelength would become larger. Now, the idea was to place this on a rotating table and rotate it in different directions that would correspond to the relative velocity of the Earth with respect to the sun. They expected to see a fringe shift. However, they saw nothing. What it told them was that the speed of light did not depend on the direction that the Earth was traveling through space. And again, this disproved the existence of an ether. Now, later on, Lorentz would come up with his transformation that would try to essentially correct for this null result and still retain the ether. But in fact, the Lorentz transformation became very, very important to special relativity, which Einstein developed later in 1905. Now, once again, the Michaelson Interferometer is very effective at measuring small distances. And it can be used to measure the wavelength of light. It can be used to indirectly measure the frequency or velocity of light if one of the other two values are known. But one of its biggest applications these days is actually in something called the Laser Interferometer Gravitational Wave Observatory, or LIGO. LIGO is actually two different observatories in Louisiana and Washington. And unlike traditional observatories, which observe electromagnetic waves, LIGO observes gravitational waves. Now, gravitational waves were predicted by general relativity. The idea is when a mass sits in space and time, it warps the space-time to create a bit of a divot, if you will. If it just sits there and does nothing, essentially space and time will also remain constant. However, if the object accelerates, the warp in space-time produces gravitational waves. In most cases, these waves are not observable. They correspond to extremely small changes in distance, much smaller than any device would be capable of measuring. The one exception of this is ultra-compact stellar remnants, which are orbiting one another. The idea of LIGO is to observe very dramatic events, such as the merger of neutron stars, merger of a neutron star and a black hole, or the merger of two black holes. And when this event happens, a huge amount of energy is released in the form of these gravitational waves. Unfortunately, these waves are very, very difficult to detect, even though they correspond to an immense release of energy into the universe. The way that we figured out how to detect them is to see how they warp space locally. And the interferometer is very effective to do this. These interferometers are massive. Typically, the beam length is measured in the order of kilometers. Think each arm length is approximately about 4 kilometers long. And as a wave propagates past these, we expect to see a very small shift in the distance along one arm, and this is detectable with the interferometer. Now, when the neutron stars merge, or when any compact body merges, again, they will spiral into one another because the release of gravitational waves means that they're giving up energy. As they give up energy in the form of these gravitational waves, they lose orbital energy and begin to spiral inward. At the last moment that they orbit one another, the release of gravitational waves is so intense that it can be detected with these observers. Now, neutron star mergers produce fairly significant gravitational waves, but probably the most intense situation is a rare merger between two black holes. When these come together, they form a new, even more massive black hole. The merger of two neutron stars, by the way, almost always results in the formation of a black hole. Now, what happens as they come together? Well, in the last day of their existence, as they're orbiting one another and they're getting closer and closer to one another, they produce these low frequency gravitational waves. They spiral inward, getting closer and closer, spinning faster and faster. And in a fraction of a second, and you can see the time down in the bottom axis right here, in a fraction of a second, they spin so quickly that they eventually merge together. And then after the merger, they actually continue to vibrate from the merger. And this is when we release the gravitational waves. Again, last second of their life. This is when they're just about touching one another. They're coming together, releasing these massive amounts of gravitational waves. And the frequency gets faster and faster because, as you know, as the orbit gets smaller and smaller, the period of the orbit gets smaller. And as they accelerate faster and faster, the amplitude of the gravitational waves also increases. Now, at the point of their merger, that's when our expectation is the amplitude of the gravitational waves will be the greatest. And then finally, after the merger takes place, the new body, which is almost always a black hole, continues to vibrate or ring for a few moments after the merger is complete. But what's so special about this is the signature of these gravitational waves is very unique. It's this chirped-like wave. It's this low frequency to high frequency wave, which becomes more intense until the point at which the merger takes place. Now, LIGO, having two observatories, can get a rough idea of the position of the event in the sky. But the reason why we also want to have two observatories is we can rule out other types of events, such as a seismic event or some other type of event, such as local traffic, in order to determine that this was truly an event that took place off in the heavens. Again, one of the observatories is located in Louisiana. The other one is located in Washington. So they're far enough away such that any local events would be can be ruled out. There's also another observatory known as Virgo, and Virgo is located in France. And by using the three observatories, if the signal is strong enough, we can actually triangulate the position of the event, and that allows us to determine where it took place. Now, when stars die, they can basically leave three different types of remnants behind, if they leave a remnant behind at all. Our sun will leave behind a white dwarf. Not very interesting. More massive stars will explode as supernova and leave behind what are called neutron stars. These are basically extremely compact objects, about the size of Manhattan, which have the same mass or slightly greater mass than our sun, between 1 and 2 solar masses. Black holes typically form at even larger masses. Black holes are the most compact of all objects. In fact, they are thought to be singularities where there is no volume. Therefore, their density is essentially infinite. We've been able to use these mergers to effectively measure the mass of the neutron stars and the black holes, because by simple understanding of gravity, we know what the gravitational period should be given the different masses of the merged objects. So LIGO and Virgo have essentially been able to establish that most neutron stars are, as expected, are somewhere between 1 and 2 times the mass of our sun. It also establishes that black holes generally are above 5 solar masses or greater. Through these mergers, we're able to make that determination. But what's interesting is we see a big gap between where the neutron stars form and where the black holes form. And this is very important in understanding stellar evolution because, once again, the most massive stars, and these are fairly rare events, usually end their lives as supernovas. Neutron stars typically end their lives as type 2 supernovas. Black holes typically end their lives as what are sometimes known as collapsars or hypernovas. Again, this is really quite unique, the Gravitational Wave Observatory, because we're detecting a type of radiation which is unlike electromagnetic radiation. It's the only other type of radiation that we can use to explore the heavens.